write down this theorem. Suppose that for every F1 in some class of PDFs P1, F1 belongs to P1. So you take any F1 belonging to P1, the test phi star is MP alpha for testing H naught that F is equal to F0 versus H1 that F is equal to F. Right? So irrespective of which F1 you take in this class P1, you get the same test as the uniformly most powerful test. Right? As it was happening in the binomial case. We saw that the given test, as long as you take any theta 1 greater than theta naught, you get the same test as the most powerful test. Right? So there this P1 was all those binomial and theta such that theta is bigger than theta naught, right? That is what class of medium. If that happens, then so that means this phi star does not depend on which F1 you have chosen in P1, right? For any F1 in P1, same test you get as a most powerful test. Right? Then phi star is UMP alpha for testing H naught that F is equal to F0 versus H1 that F belongs to P1. Right? So it is simple versus composite. Now note that if this test was such that if supremum over there was a some class P0 in which F0 belongs, and if supremum over that class P0 of beta phi is also less than or equal to alpha, then that test would be uniformly most powerful for testing that F belongs to P0 against F belongs to P1. Is that okay? So, so let F0 and F0 belong to P0 and F1 belonging to P1. So just let me pause for a while. You see, when you enter and ask, may I come in, you disturb me twice. First, when you're entering, and second thing, you're asking me, may I come, right? So don't do that. You can always walk in, right? You don't have to take my permission. Right? So let F0 belongs to P0 and F1 belongs to P1. And alpha is 0 to 1. There, this P0 and P1 are disjoint class of PDFs, right? So suppose that phi star is UMP alpha for testing H naught that F is equal to F0 versus H1 that F belongs to P1, right? Now this kind of a situation can come from theorem 1, right? As it was happening in the binomial case. Now if supremum over expected value of phi star over F belonging to P0, you see the only issue would be because I know that in terms of power, let me come to the proof one by one. If supremum is less than or equal to alpha, then phi star is UMP alpha for testing H naught that. Which one? Supremum over F belonging to P0. Yeah, F, yeah. There is no theta over here. For testing that F belongs to P0 versus H1 that F belongs to. So you see, the idea is very simple. I have explained this. In fact, I have given the whole proof through that example, binomial example. So you see, what happens is, to begin with, you have a test phi star, which is most powerful for testing F is equal to F0 against F is equal to F1. That you can get through the Neyman Pearson lemma. Now, suppose this F1 was belonging to the P1, and this UMP, this most powerful test which I get, does not depend on F1. It is the same test for every F1 belonging to P1. Then what happens? Then basically what I'm doing is, whatever F1 you take, the power of this test would be larger than any other test. So that means it is maximizing power for every F1 belonging to P1, because my test does not depend on F1. Which F1 you have chosen in P1, my test does not depend on that. As it was happening in the binomial case, what we saw was, when you're determining that test has 1 if summation xi greater than c, gamma if summation xi is equal to c, 0 if summation xi less than c. And how this gamma and c are determined? So that probability under theta naught, summation xi greater than c plus gamma times probability under theta naught, that summation xi is equal to c is alpha, right? Nowhere theta 1 is coming, because this gamma and c depends on what theta naught is. Theta 1 is coming only through the fact that my critical reason that summation xi greater than c would have converted into summation xi less than c if theta 1 was not bigger than theta naught, it was less than theta naught. So that means I'll get the same thing as long as theta 1 is greater than theta naught. So in that case, what does my P1 becomes? It is binomial, all those binomial and theta such that theta is greater than or equal to theta naught. For all such thetas, I get the same test, phi star. So that means that test becomes uniformly most powerful for testing F is equal to F0 against that F1 belongs to P1. That means theta is bigger than theta naught. Is that okay? So this follows just from here. And I have explained the proof. Let us look at this situation. Now I have reached over here. Let us again go back to the binomial example. So I have taken care of the power, because that is, in terms of power, F is in P1, so it is the same P1 over here. So in terms of power, I know, or in terms of our type 2 error probability, I know that this test has a minimum type 2 error probability. But to make it MP alpha, I have to make sure that expected value of phi star under H0 is always less than or equal to alpha. If that happens, then my purpose is served. So that means the only thing I have to make sure is supremum over F belonging to F0 of expected value of phi star is less than or equal to alpha. Then such a test would be uniformly most powerful for testing this composite hypothesis, F belongs to P0, against that F belongs to P1. Right? So simple. It's simple observation. That's all. Okay, so let us do now a generalized Neyman-Pearson lemma, which may be useful in certain situations. So let me write down that as a lemma. So what you're having in the usual Neyman-Pearson lemma was, you're having just two hypotheses, F0 and F1. Now you may have more than one hypothesis, H0, H1, H2, and Hm, right? So that means you may have M plus 1 PDFs, right? F1, F2, M plus 1. So let F1, F2, Fm plus 1 be real valued functions on RP. On RP. P-dimensional Euclidean space. Now note that I'm not assuming that they are PDFs, right? They can be anything. There are any functions. So it's a more mathematical lemma than a statistical lemma. So F1, F2, Fm plus be real valued functions defined on RP for given constants alpha 1, alpha 2, alpha p. Note that in terms of original Neyman-Pearson lemma, these alphas were labeled. I'm not assuming anything about alphas. They are just any constant, right? let I consider two class of test functions. One class is D. D is collection of all those phi's, such that phi is a function from Rp to 0, 1. And integral over phi x, fix dx is less than or equal to alpha. So it is like a collection of all those tests for which level is less than or equal to alpha. Except that now here you have a p hypothesis, integral over f fi. And d naught is collection of all those phi's, such that phi is from Rp to 0, 1, such that this quantity is exactly alpha. Which class is a bigger class? Anyone? D0 or D1? Yeah, because if this happens, any phi which happens here also belongs to this because it is less than or equal to alpha. Right? So certainly D0 is contained in D. Now, if there are constants, C1, C2, Cm. Note that in Neyman Pearson lemma, I required Ci's to be greater than or equal to 0. Here, I'm not doing anything about Ci's. So if there are constants C1, C2, Cm, such that phi star x is 1 if Fm plus 1x is bigger than summation I is equal to 1 to m Ci Fix, and 0 if Fm plus 1x is less than or equal to this, is a member of D0. Is a member of D0, that means level is less than or equal to alpha is. Then phi star maximizes, its power is maximum, integral over phi x Fm plus 1x dx over phi belongs to D naught. Now, if these CIs were such that they are non-negative, then this would maximize, in fact, this quantity over D. Okay? So if CIs are greater than or equal to 0, then phi star maximizes integral over phi x Fm plus 1x dx over D over a larger class. So it is, if you try to match it with your Neyman Pearson lemma, it is exactly same as Neyman Pearson lemma, except that in the Neyman Pearson lemma you had only F0 and F1. So actually this your Fm plus 1 is playing a role of F1 and F1. So I could have used better notations that I could have written down F0, F1, Fm plus 1, right? That's okay. So Fm plus 1 is playing the role of, in this Fm plus 1 is playing the role of F1, and F0 is basically whatever is Fm. There are only two, right? So you want me to write down that way so that you don't get confused? It's okay, right? So I think that understanding you have. So otherwise it is exactly same. So the proof also has to be same. Do you recall how I had done the proof? I have to show that this is maximum. Right? So I consider any test phi belonging to D0, right? And then I show that integral over phi star Fm plus 1x minus phi that is greater than or equal to 0, right? That is what I try to show. So let phi be any test belonging to D0. Okay. What I have to show is phi star integral over phi star fm plus 1 dx would be greater than or equal to integral over phi fm plus 1 dx. All what I had done, I had treated this as, I consider delta x, which is nothing but fm plus 1x, or you can write down phi star x minus phi x into fm plus 1x minus summation I is equal to 1 to m ci. Is that okay? What can you say about this quantity? So you see, when fm plus 1 is bigger than summation ci fi, the second term is positive. But when that happens, phi star is always 1 and phi is always less than or equal to 1. So both positive. So it is anyway positive. When it is exactly equal to, then it is 0. When that quantity is fm plus 1 is less than summation ci fi x, the second quantity is negative. But in that case, phi star is 0 and phi is between 0 to 1, so it will be bigger than 0. So that is also negative. So whatever may be the case, this is always positive. And exactly that is what we had done while proving the Neyman Pearson lemma. So nothing substantially new. It's exactly same, except that I have added few more PDFs. Now you know that if a function is non-negative, then its integral has to be non-negative. So this means integral over delta x dx has to be greater than or equal to 0. Because this is happening for every x. If a function is non-negative for every x, then its integral has to be non-negative. Of course, this is a m-fold integral, right? P-fold integral, because these x1, x2, xp are p variables. What does that mean? That means integral over phi star x minus phi x fm plus 1x. The one thing over here would be greater than or equal to summation I is equal to 1 to m. This would be I is equal to 1 to p, I guess. I is equal to 1 to p. You can make it p because there are p only, right? F1. No, m, yeah, m is okay. I is equal to, because m functions, yeah. Ci integral over phi star x minus phi x into fi x. Is that okay? Because this integral is positive, so 1 I combine with fm plus 1, which is this quantity, minus that is greater than or equal to 0, so that I take outside. Ci's are constant, they'll come outside the integral, and you get this. Is that okay? Yeah. Yeah, there's m and p's you can just write. Interesting. What is this quantity? Integral over phi star x into fi. Phi star is an element of D0. Phi star is an element of D0, that means integral over phi x is same as alpha. So this would be alpha minus. What is happening over here? Phi I have taken to be an element of D0 because that maximizes over D0, that is what I have to show. So that is also same as alpha. So integral over phi star x fi x dx is alpha, and integral over phi x dx is also alpha. So this becomes 0. So it becomes summation ci times 0. Each term becomes 0 in fact. So what do you get? This implies that integral over phi star x fm plus 1x dx would be greater than or equal to integral over phi x fm plus 1x Thanks. And that is what we were required to prove. That you take any other element in D0, try to show that integral over phi of that would be smaller than the corresponding thing with phi star. Is that okay? Now note that it says if CIs are non-negative, then phi star maximizes this quantity over a bigger class, which is D. That is also very trivial. Up to here, the proof would be same. Now this phi is in D, because I have to show that phi is in D, because phi 0 is anyway in D. Because phi 0 belongs to G0, so it belongs to D. So I take any element in D. In that case, what happens is this quantity would be alpha only, because my phi star, the way I have chosen phi star is always in D naught. Right? My phi star is in D naught. But then what would be this quantity? Integral over phi n. This would be less than or equal to 0. No, this would be less than or equal to alpha. This is alpha, this is less than or equal to alpha. So that means this would be positive. So if CIs were also positive, a positive quantity multiplied by positive would be always positive. So that is why you need CIs to be greater than or equal to 0. So in that case, also the proof is straightforward. Right? So nothing very great about it, but we may need this theorem while we are doing some advanced topics and hypothesis testing. So I thought that we can do it right away. So if you recall that example of a binomial distribution which we did last time, we could find the UMP alpha test for proving theta is equal to theta naught against theta greater than theta naught, right? Just using Neyman Pearson lemma. But I had left it at the point that this test would also be uniformly most powerful alpha test for testing H naught theta less than or equal to theta naught against theta greater than theta naught. Same test. But I did not prove it. Right? I said the proof would be possible only when I can prove that supremum over theta less than or equal to theta naught of expected value of phi is less than or equal to alpha. Right? That is what I needed to prove, and I could not prove it. So now I'll kind of prepare a ground for proving such a thing. Now, there is something called monotone likelihood ratio property, right? Have you heard this name before? Monotone likelihood ratio? Okay. So first let me give you a statistical sense of such a concept. And then let me define what is a monotone likelihood ratio property. Have you ever realized when you decide a test, when does a critical region become X bar greater than C and when it becomes X bar less than C? Has it ever bothered you that you look at the test and immediately they say that I'll reject for X bar greater than C? Why not for X bar less than C? Are you clear what I'm asking, first of all? Is the question clear which I'm asking to you? So how do you sell that concept that, look, no, I'm rejecting only for large values of X bar, not for small values of X bar. How will you sell that to a person who has very little knowledge about statistics? How will you sell it? So for example, normal, right? Normal, you have to test normal theta is equal to 0 against theta is equal to 1. Theta is a mean. You say I'll reject for X bar greater than C. My question is, why not for reject X bar for X bar less than C? The answer is simple. You see, I'm trying to provoke you to answer this question so that you can understand monotone likelihood ratio in a better manner. You'll be able to appreciate it more. Why? Because you see, you don't know what the mean is, right? Population mean you don't know. The only information available to you is the sample. So I want to extract information from the sample about the population. Now here it is a population mean, so X bar looks like a sample mean. So it looks like if my sample mean is larger, that is an indication that my population mean would also be larger. But how do you define it mathematically or statistically? That is, your intuition is all right that even somebody who is totally illiterate and sitting in IIT Kanpur gate. Also, yeah, that makes sense. There are two populations. One population has a larger mean and one population has a smaller mean. You are taking sample from both then it is expected that the population which has a larger population mean would yield a larger sample mean. Right? That is very. But how do you define this concept mathematically? Sample mean is a much easier concept to digest. There will be much more complicated statistics. So basically, one way to do it is everything is stochastically. You see, there's still a possibility that that mean is larger. So suppose I have a population on one side and I have a population on this side. So suppose the average CPI of people on this side is larger than the average CPI of this. So these are population. So I expect that if I take a sample from here of size 2 and size 2 over here, the average CPI of people over here would be larger than the average CPI of people over here in the sample mean. But there is an expectation, right? And statistics, you always talk everything in terms of chances of that happening. Because there is still a chance that whatever sample I take, the sample mean there may be larger than this. So how do you define that? So everything has to be done in terms of either probability or expectation or something. So what it means is so if I have a statistics T, let me write down stochastic increasing property. So suppose I have a random sample x1, x2, xn. These are random sample. So RS stands for random sample from some PDF or PMF f theta. Where theta takes values in some parameter space theta, which is a subset of R. Tx is some statistics. Tx was sample mean in the example I just quoted. So if I have to define that larger values of theta get captured in Tx through larger values of T, that means larger values of theta lead to larger values of T. How do I define that? Because everything in terms of probability, in actual reverse may also happen. So one way to do that would be for every T belonging to T, suppose for every small t belonging to T, probability that theta 1 Tx greater than T is less than or equal to probability under theta 2 Tx greater than T for every theta 1 less than theta 2. What does it mean? That means here theta 1 is less than theta 2. So if theta 1 is less than theta 2, then probability that Tx would be taking value larger than T would be smaller than the probability that Tx would be taking larger value than the same threshold T under theta 2. So that means for larger value of theta 2, because theta 2 was bigger, probability that Tx take a larger value for a given threshold would be larger. This looks like a very natural way of defining it, right? Now, if that happens, I say that Tx has a stochastically increasing property. We say that Tx has, or f theta belonging to theta has stochastically increasing property. Increasing property in Tx. In statistic T. It can hold, it may not hold, right? Equality means they are same distribution, right? Under theta 1 and theta 2, the distribution is same, right? The equality would hold, what does that mean? Huh? Doesn't matter, you left for continuity, even if continuous case, there will not be any problem. Because then it is saying that distribution function of that would be same as distribution function of that. See, this is same as 1 minus probability that Tx less than or equal to T. Na? 1 will get cancelled both the sides. So to become a distribution function of Tx under theta 1 is same as distribution function of Tx under theta 2. So what does that mean? That means under theta 1 and theta 2, distribution of T is same. So it does not depend on theta. Right? So you see, if such a property holds, it gives me an indication that larger values of thetas are getting captured in Tx through larger values of T. That means if I have to test a hypothesis theta is equal to 0 against theta is equal to 1, alternative is theta is equal to 1. So what is the alternative hypothesis? Where theta is large. And how the larger values of thetas are getting captured into T? Through larger values of T. So this suggests that my critical region should be rechecked if T is large. Right? So Tx greater than C. Is that okay? One can talk about stochastically decreasing property when this inequality changes. That means larger values of theta correspond to the smaller values of T. Right? So if one can determine that, finding a critical region would be all right. But normally verifying this condition is very difficult because you know that your distribution function can be very nightmarish to handle, right? Sometimes it may not have a closed form and then be very difficult. So can we find some easy way to verify this condition? And one such property is called a monotone likelihood ratio property. So let me give that, and that would be very easy to verify in terms of the PDFs, because that would be in terms of PDFs. And normally PDFs are in closed form. So let me define what do you mean by the monotone likelihood ratio property. So I have a P, which is a family of PDFs. This is a family of PDFs. Here theta is a subset of real line. Tx is some statistic. P is said to have monotone likelihood ratio property in Tx, in the statistic Tx, if for every theta 1 less than theta 2, theta 1, theta 2 belonging to the parameter space theta, when you look at f theta 2x upon f theta 1x is increasing in Tx, for all x where at least one of them is positive, right? For all x as that collection of all those t, says that f theta 1 t is positive, or collection of all those t's says that f theta 2 is positive. So at least one of them should be positive. So if that thing happens, then I say that your PDF has a MLR property. Can you give me examples of distributions having MLR property? But before that, let me prove a result. So certainly, MLR implies SIP. That if your statistic has a MLR property, it would be stochastically increasing. Let me not prove it over here. One can prove it, but I think it's more important to know the result rather than proving it, because this course is mainly on testing, so I don't want to get into a domain where I just spend a lot of time in. Proof is not complicated, but just note the fact that MLR implies SIP. So I would not bother that much about SIP. I would bother about MLR because that would be normally very easy to verify. Now, let us look at if you have an MLR property. Then what can you say about expected value of Tx under theta 1 and theta 2? So I have E theta 1 Tx and E theta 2 Tx. Which one should be larger? E theta 2 Tx would be larger, right? Because I know that MLR implies SIP. If there is a SIP, that means larger values of T's are corresponding to the larger values of theta. So that means if I take expected value of T under theta 1, that would be smaller than expected value of T under theta 2 if theta 1 is smaller than theta 2. Why only T? Take expected value of any increasing function of psi, increasing function of T. So E theta 1 of psi of Tx would be less than or equal to E theta 2 of psi of Tx. And that is the next result, which I'll write it down over here. So lemma. Suppose that my family P, which is F theta, theta belongs to capital theta, where theta is subset of R, has MLR in Tx. Various statistics in which it has a MLR. If psi is any non-decreasing function, any non-decreasing function, then G theta, which I define as E theta of psi of Tx, is non-decreasing function of theta. So note that if you just write down this, if you try to understand this as a mathematical statement, it may look scary. But if you understand what it is saying is, you'll find that what it's saying is a trivial thing. Because my PDFs have a MLR, which suggests that larger values of thetas are corresponding to larger values of T. And if that happens, then suddenly I expect that expected value of any increasing function of T would be larger for larger values of theta. Exactly that is what it is saying, nothing else. So let's try to prove this. If psi is an increasing function, so what I need to show is G theta 1 would be less than or equal to G theta 2, provided theta 1 is less than theta 2. So let theta 1, theta 2 belonging to capital theta be such that ST stands for such that theta 1 is less than theta 2. Then I have to show that G theta 1 is less than or equal to G theta 2. So I define 3 different reasons. A as collection of all those x such that f theta 1x is greater than f theta 2x. B as collection of all those x such that f theta 1x is less than f theta 2x. And C is the reason where they are same, that you can include in any one of them. Small a is a supremum over x belonging to A of psi of tx. B as C you can define as collection of all those x such that f theta 1x is same as f theta 2x. And I define B to be infimum over x belonging to B of psi of tx. Can you tell what would be a relationship between small a and small b? Small a is collection of all those reasons such that f theta 1x is bigger than f theta 2x, or f theta 2x is f theta 2x upon f theta 1x is less than 1. And this is a reason where f theta 2x upon f theta 1x is bigger than 1. Right? So let us look at f theta 2 upon f theta 1 is increasing in t. So this reason that f theta 2x upon f theta 1 is less than 1 will be equivalent to saying that tx is less than some constant, because f theta 2 upon f theta 1x is increasing, so they will preserve the same inequality. So this reason is same as tx less than c. What would be this reason? In this reason, tx would be bigger than c, some constant. So that means whatever tx you have is always bigger than the tx over here. Or in particular, the maximum value of tx over here would be smaller than the smallest value of tx over there. So that is what it says. A is supremum over x belonging to A of psi of tx, and infimum over this. So A is less than or equal to B. This is due to the fact that f theta 2x upon f theta 1x is increasing in tx. Yeah. So I have defined A to be the supremum of values of psi of tx over this set. When I look at this set, what is this set? This is a collection of all those x such that f theta 2x upon f theta 1x is less than 1. And because your family has a MLR, so f theta 2 upon f theta 1, because theta 2 is bigger than theta 1, is increasing in t. So f theta 2 upon f theta 1 less than 1 set would be same as tx less than some constant c. It would be tx bigger than the same constant. So here tx is smaller than that constant, and whatever tx we take over there, that is bigger than that constant. So whatever tx you take over in this region would be larger than the tx over here. That means even the largest tx over here would be smaller than the smallest tx over there. Is that okay? Okay. Once you have done that, then the proof is straightforward now. Now you can write down g theta 2 minus g theta 1 and break it into 3 parts. So g theta 2 minus g theta 1 is same as expected value of psi of tx minus e theta 1 of psi of tx, which is integral over psi of tx into f theta 2x. In the case of discrete, it would be a summation sign, right? Integral over psi tx This was expectation under theta 1, so density under theta 1. Which is same as integral over psi of Tx f theta 2x minus f theta 1x. All right. I break this integral into three parts, A, B, and C. C, in the C part, f theta 1 is same as f theta 2. So this would be 0, and that will not be contributing anything, right? So this would be same as integral over A psi of Tx into f theta 2 x minus f theta 1 x dx plus integral over B of psi of Tx f theta 2 x minus f theta 1 x. Okay, what can you say about this quantity? Over A, what is happening to f theta 2 minus f theta 1? Less than 0, right? So this quantity is less than 0. Over A, what is the maximum value of psi Tx? Small a, because small a is the supremum of psi Tx over A. And so this would be less than or equal to A. Let us look at this quantity. F theta 2x minus f theta 1x over B is greater than 0. And this would be greater than, because A is the infimum. So this would always be greater than or equal to A. So what do you conclude from here? Here this is less than or equal to A, and I'm multiplying it by a negative quantity. So inequality would get changed, right? So this would be greater than or equal to A times integral over A f theta 2x minus f theta 1x plus, here both things are positive, so inequality doesn't change. So it is same as, so let me write it down, the next one. I'm done. So plus 8, plus, both the, no, this would be, I've written on that as B, right? B is the infimum. So this is greater than or equal to B. Plus B times, yeah, B is also greater than or equal to A. So that you can use later on, but for the time being, just let me write it down this quantity. Integral over B f theta 2x minus f theta 1x dx. Is that okay? But what is the integral over A f theta 2x minus f theta 1x plus integral over B f theta 2x minus f theta 1x? Both are PDFs. Both are PDFs. So integral over f theta 1x or f theta 2x minus f theta 1x dx would be 0, because both of them are value 1. That means integral over A plus integral over B of this quantity would be 0. Right? So what does that mean? That means integral of over A would be same as minus of integral over B of that quantity. So this is same as B minus A integral over B f theta 2x right? Because total integral is 0. I can break it into three parts, integral over A plus integral over B. Integral over C, f theta 1 is same as f theta 2, so that anyway would be 0. So integral over A plus integral over B is 0. So that means integral over A of this quantity would be same as minus of integral over B. And that gives me this. But in B, what is happening to f theta 2x minus f theta 1x? Greater than 0, right? That is what in the region B. And B minus A is anyway greater than 0. We have seen that. So positive multiplied by positive is getting a positive. So that proves that a very important result, which basically is guided by your intuition. When written in a mathematical form, it looks slightly complicated, but what it conveys is a very simple thing. That if your family of PDFs have a MLR, what does that mean in statistical sense? Larger values of theta are corresponding to the larger values of t's. Then larger values of theta would correspond to the larger values of expected value of psi of tx for any increasing function psi. That is what exactly this whole theorem is saying. Right? So if you try to analyze this statistically, everything is very simple. Right? Of course, if you have a maturity, you can write down that in a very nice mathematical form. And that is what I did in today's lecture. So tomorrow we'll discuss these homework problems, which I gave you as assignment number 6 or 7, whatever it is. Yeah. Huh? I don't.